Okay, so it's our pleasure to have Michael Forbes giving a talk today. So he'll be talking to us about explicit dimension reduction for varieties and PIT. Michael, the floor is yours.
All right, thanks for the invitation to speak. Yeah, so that's my talk. And so what I'm going to do today, first I'm going to talk about the polynomial identity testing problem, and I'll abbreviate that as PIT. Kind of like what is it and why is it important? Obviously, I can't cover everything, but kind of cover the basics. And then I'll try to relate PIT to dimension reduction for varieties in the sense of the nether normalization lemma, at least one version of the lemma, which I'll define. And then I'll apply that to simultaneous conjugation of matrices, which is a group action that has somewhat appeared already in this school and kind of is related to invariant theory, which was topic of several earlier lectures. Okay, so let's start with the definition of polynomial identity testing. And as you can see, my handwriting is not the greatest, so if there's something that's unclear, please do stop me to clarify. Okay, so what is the polynomial identity testing problem?
Is there a way to expand it? Actually, I can't see much. Can I do it, or you will have to do it? I don't know.
Expand, like make it larger?
Make it larger, a bit larger. Is it possible, or I don't know.
I've not had problems when I've done this on other forums. I can write larger. I don't know how to make it larger.
Sure. Can you just write a bit larger? Yeah, I mean.
Yeah, that's fine.
Yeah.
Okay, so given a polynomial f, we want to know is f equal to 0. Okay, and so in the sense that we want to know, is it identically, we're testing whether this polynomial is identically equal to 0. So hence polynomial identity testing. But there's a lot of subtleties in just saying what is this problem. So first of all, what is f? So f is going to be a multivariate polynomial. So this is a sum over exponents a. We have some coefficient in the field, and so I write vectors with a bar on top. And so this is a exponent vector. And then we have a monomial x to the a. And this monomial x to the a is just the product I from 1 to n of xi, ai. Okay, so this is the exponent vector in the n variables. So you see here that n is the number of variables in our polynomial. So it's a multivariate polynomial. And we also have to ask, what does it mean to be given a polynomial? And so here we're saying that f is given via an algebraic circuit, which I abbreviate as CKT, of small size at most s. Okay, and so we've seen what are algebraic circuits, and there are other models that one can consider, formulas and so on. And we'll also be assuming here that degree of f is at most d. And so the parameters that I'm dealing with are, size, the number of variables, and the degree d. And so that's the question. I'm giving you a circuit using additions and multiplications to specify a multivariate polynomial of this form with coefficients in some field, and we want to know, is it just a 0 polynomial? And we'll say that a PIT algorithm is black box. If what? If it only uses the circuit to evaluate the underlying polynomial f at chosen points. Some betas in f to the n. So basically, a black box algorithm would say, well, you're giving me the circuit, but all I'm really doing is using the circuit to evaluate this polynomial at multiple points, beta 1 up to beta whatever. And if it's black box, if it only basically is treating the circuit as a black box, it's not looking inside how we're actually computing the polynomial. It's just using that polynomial to the circuit to actually compute the polynomial, and not looking at the structure of the circuit. And we'll otherwise say, if it's not of this form, it's white box. Okay, so this is the algorithmic question that I want to talk about today. And how do we solve this? Well, let's first see some easy lemmas. So first of all, PIT has a polynomial in n plus d choose d and s time deterministic algorithm. Okay, so what are these parameters? S, right, is the circuit size. N plus D choose D is the number of monomials that can occur in a polynomial of this form. And what's the proof of this? Is we're just simply going to expand each of the S operations. Right, so we have an algebraic circuit of size S, and so there are S additions and multiplications and so on. So expand each of these operations, the result of each of these operations, into the N plus D choose D monomials. Okay, so all the intermediate computations would be, at least up to homogenization, would be of low degree. And so you can just simply expand all of the intermediate computations into these monomials, into this monomial basis, and that's why you're getting this term. And then you have S operations, and that's why you get this term. I guess I realize that. Thinking about now, you need to homogenize the circuit first, but that's something that was kind of seen. Okay, so this is saying basically that there is an algorithm that can run in some amount of time. But is this good or is this bad? So let's look at the parameters. So N is the main parameter, it's the number of variables. And so here we're thinking of this as large. Okay, so N kind of going to infinity or something. All right, D is the degree. And typically we'll sort of think of this as at most some polynomial in N. So it's not too small, it's not constant per se, but it's also not too large. It's not exponential in N. And then S again is the size of the circuit. And also we'll be thinking of this as something polynomial, something of medium size. And so if we look at kind of this regime of parameters, then this algorithm is not particularly great in the sense that N plus D choose D is exponential. And so it's an exponential time algorithm, so it's not efficient in the way we would want. Okay, so there is some deterministic algorithm, but then we can ask, is there an efficient algorithm? Maybe not necessarily deterministic. Okay, so so let's see the Shortstop Dilemma as a way to get an efficient algorithm. This is something that is mentioned at least once by Avi in school so far. So suppose that we have a subset of our field, and we have a polynomial which is non-zero. And so I'm not necessarily going to be specifying, but it's usually an n-varied polynomial, degree t, and so on. The size is maybe not in this case important. Then what happens if we evaluate f at a random point? So I'm going to choose alpha at random from s to the n. So this is an n-coordinate tuple because this is an n-varied polynomial. And if I choose randomly from this cube, I want to know what's the probability that f at alpha is equal to 0. Okay, so this is a bad event in the sense that f is non-zero, but we're asking what's the probability you evaluate to 0. And this is going to be at most d divided by the size of s. So this can be proved by induction on the number of variables based on the number of roots of a univariate polynomial, for example. But the point is that if we let s, the size of our set in our field, to be like twice the degree, then this is at most 1/2. And so the corollary of this would be that PIT has a polynomial in n, d, and s time randomized algorithm. Okay, so basically just run this algorithm by just evaluating your polynomial at a random point, and notice that we only use the circuit to evaluate the polynomial, and so this is in fact black box. Okay, so the point is that with this result, we get two interesting things as compared to what happened on the previous slide. Right, so in the previous slide, we had, first of all, that this was actually white box, right? If we're expanding each of the intermediate computations into their monomial basis, we're actually looking at how the polynomial is being computed. So this is a white box algorithm, and it's inefficient. Okay, but when we go back over to here, we're getting something which is now efficient. And it's black box, which is a stronger solution concept because we're only using the circuit in a weaker way, and so it's a stronger algorithmic result. Okay, so there is a randomized algorithm that's efficient and black box. The one thing that's missing from this would be to say if it's actually deterministic as compared to what would happen on the previous line. Okay, so this is saying that we can solve PIT in some sense efficiently. And then the question would be, why does this matter? So what are the remarks on this problem? So first of all, PIT is a powerful algorithmic tool. So just solving this problem, it captures a lot of what's going on in interesting ways in algorithms. And so what is the most obvious way of looking at the power of PIT would be from computer algebra, in the sense that we want to come up with algorithms to manipulate algebraic expressions. So the most obvious application would be just verifying polynomial identities. So for example, we could consider the determinant of AB, two square matrices, the product of two square matrices is the determinant of A times the determinant of B. This is multiplicative of the determinant, which is something that we learn in linear algebra. And there's a proof of this, that uses, say, for example, Gaussian elimination. But if you just wanted to prove this without really knowing anything about linear algebra, all you need to know is that the determinant is officially computable, which I guess requires linear algebra. But to prove this identity, you could just use some sort of Polynomial identity test, as opposed to thinking hard about mathematics. So that's the obvious thing. If I just gave you an expression like this, is the left-hand side equal to the right-hand side? That's, if you look at the subtraction, is it 0 essentially? But maybe a less obvious thing would be basically any efficient manipulation of succinct algebraic expressions. Okay, so checking whether two things are equal is asking whether the difference is 0, right? So that's just a 0 testing question. But are there more sophisticated things we can try to ask and solve with PIT? Well, one example would be, for example, checking if f divides g. Okay, so this doesn't obviously seem like a 0 testing question. But basically, suppose I gave you f as an algebraic circuit and g is an algebraic circuit. I want to know, does f divide g? Or in this example, does the determinant of a divide determinant of a times b? It does in this case, right, because of this identity. And if you wanted to check this, the obvious thing to do would be to expand it into the monomial representation and then do long division, right? That is an algorithm. But because it's multivariate, it's not going to be efficient. It's going to be exponential time. But the point is that even though this doesn't seem like a 0 testing question, you can convert it to 1 and use PIT to solve this. And so there's some idea that most things that you're interested in terms of taking an algebraic circuit and asking some property of it can be reduced to PIT in some form. Okay, so computer algebra is like kind of an obvious application because it's very much in the sense of PIT. But there are also sort of non-algebraic problems that can reduce the PIT kind of non-trivially. And so one would be famously deterministic formality testing, which, while in some sense, and this is due to Agrawal, Kyle, and Saxena, while in some sense this is algebraic, and it's really more like a number theory question, although there's algebra there, but it does reduce to PIT, and that's how we know that we can deterministically check whether, and efficiently check whether a number is prime or not. And then there's something that has been mentioned several times, is that there are parallel algorithms for graph matching. I give you a graph and you want to know, is there, say, a perfect matching, if maybe it's bipartite or whatever, and maybe in particular case you want it to be a parallel algorithm, you can reduce questions about graph matching to questions about polynomial identity testing. And this is due to things like people like Lovash, and very, in the past 5 years, it's been actually somewhat de-randomized by very nice work of Fenner, Kujar, area. And so the only way we really know of parallel algorithms for graph matching is going through this PIT connection. Even though there are many nice combinatorial algorithms, they're not necessarily parallel. And so we're seeing PIT plays this really nice role in obtaining these sorts of parallel algorithms. Okay, so how should we think about PIT? right? There's this white box and there's black box. I think for people outside the field, maybe the white box versus black box is a little bit hard to appreciate. But I do want to emphasize that black box PIT is really a stronger solution concept, in the sense that our algorithm is more restricted. So if you obtain an algorithm in this restricted model, it's a stronger result. And it's important for some applications, some of which we'll see today, that if you attain a black box algorithm, sometimes it can do more than a white box algorithm could do. And that's something that we'll kind of see a little bit today. Later. Finally, there's kind of one of the interesting reasons for studying PAT is there's tight connections, as I'll mention later, to proving lower bounds. So understanding lower bounds, like is the permanent, does it have a small circuit? That has a very tight connection to whether you can de-randomize polynomial identity testing. And so there's some idea that, well, if you want to study the lower bounds question, you could also study the deterministic polynomial identity testing question, and those are in some sense tightly related. And one of the reasons that this is very interesting is because proving lower bounds is like an impossibility result, saying that something does not have a small circuit, whereas PIT is a possibility result. De-randomization is a possibility result designing some sort of algorithm. So there's some idea that sometimes algorithms are easier to develop. Okay, so that's just some perspective on kind of like why we might want to be studying this problem. Okay, so I want to elaborate more a little bit about the black box definition. So suppose that you have a class curly C of polynomials, of n-varied polynomials, so it's x bar. So this is some class of polynomials. We're going to say that curly H, which is a subset of n tuples, is a hitting set. If what? If for all f in curly C in our class of polynomials, we have that f is a non-zero polynomial if and only if f at alpha is non-zero for some point alpha in curly H. Okay, so we want to decide, for example, whether f is 0 or not. And we're saying all we need to do is just evaluate f on all of the points in our hitting set, and f will be non-zero if and only if one of those polynomials will be, one of those evaluations will be non-zero. Okay, and why am I defining it this way? Well, there's a lemma, which is to say that if you have deterministic t-step black box PIT algorithm for some class curly C, this is equivalent to a hitting set H for C, where the size of our hitting set is at most T. Okay, so black box algorithms are just saying, oh, okay, all we're doing is we're just evaluating the polynomial a bunch of black box algorithms are just ones that evaluate the polynomial on points and make some decision based on that. But possibly there's some adaptivity going on, like you make some decisions about new points based on information you have from old points. But it turns out that that's actually not the case, that hitting sets are exactly what deterministic black box algorithms are. And it's not too hard to see this in the sense that if you have a hitting set, then just evaluating on the hitting set is a deterministic black box algorithm, where the runtime is just basically the number of evaluation points. So the backwards direction is easy. The forward direction is not hard. Basically just proving you can remove the additivity. So when I talk about black box algorithms, I mostly will be talking about hitting sets and the size of those hitting sets. Okay, so then do hitting sets exist? Well, we haven't seen any deterministic algorithms, so we can't use this connection as is, but we do have the following, that if you have a subset of the field and the size of your subset is at least d plus 1, where d is the degree of the polynomials that we're interested in, then this cube, s to the n, is a hitting set for curly C, which is the set of n-variate degree at most d polynomials. So we're not actually restricting the size bound in any way. Okay, and so what is the proof of this? This is just the Shortstop Dilemma. The Shortstop Dilemma says that if you have a non-zero polynomial and n variables at degree at most d, and you evaluate on this cube, then with non-zero probability, it will actually be a non-zero evaluation. And so we just, instead of thinking about a probabilistic statement, we just think about an existential statement, and then that shows that this is exactly a hitting set of this form. Okay, so this is an exponential size hitting set in the sense that we have d plus 1 to the n is the size of our hitting set. And so this is an exponential time deterministic black box algorithm. And again, it's worth comparing that we can compare this to the exponential time white box algorithm that we saw earlier, in the sense that it's about the same runtime, but now it's black box instead of white box. And instead of the Shortstop Dilemma where it's randomized, this is deterministic. But what about efficient black box algorithms, right? Are there small hitting sets? And so this is kind of a non-trivial question. If we want to construct small hitting sets or construct efficient black box PIT, we need to say that, hey, hitting sets actually exist. And so there's a theorem of Heinz and Schnorr, which says that there exists, non-constructively, a polynomial in n, d, and s size hitting set for curly C, where we have n variables, degree at most d, and size at least s, when the size of the field is at least some polynomial in n, d, and s factor. And so this is saying that there exist small hitting sets, but it's not necessarily telling us how to find them. It's a non-constructive result. And so what's the sketch of this? Just to get a sense, it's kind of similar to sketches for why there are hard polynomials, sort of a probabilistic method argument. So let's just start with the idea for a single non-zero polynomial f. What happens if we take many random points? Well, from the Shortstop Dilemma, we know that if we take alpha 1 up to alpha t in some cube where the cube is suitably large, maybe s greater than 2d, then the probability that all of these evaluations are 0 is at most d over s to the t, right? So if d over s is at most a half, for example, then this is exponentially small in t. Every point that we have that we add is making this drop by a factor of 2. So this is the Shortstop Dilemma applied to many independent random evaluations. And since this is exponentially small, we can in some sense think it's 0. It's not actually 0, but it's exponentially small, which is small. Okay, so this is saying for a single point, we take many random evaluations, it will be non-zero with extremely high probability, probably close to 1. The probability of error is very small. So what we can do instead is that we can apply a union bound over all f with a small circuit. So this is saying for one circuit, there's something, a random set is a hitting set with very high probability. And now we apply a union bound. And how do you apply a union bound in this case? Well, if f is finite, you can simply count small circuits, right? In the sense that there's at most exponentially many of them, and hence if you multiply it by something exponentially small, it's going to be at most 1.5, and hence a hitting set will exist. What's more interesting in the context of this school is what happens when f is infinite. If f is infinite, then we can't use a counting argument because there's an infinite number of circuits, and so it's not going to work, right? Because you have an infinite number of things battling something which is exponentially small, and the infinite will always win. Okay, and so what you have to use instead is that you use that curly C, the set of polynomials and n variables, degree at most d, in size most s, is contained in a small dimensional variety. Okay, so it's still a counting argument, but instead of counting things in terms of numbers, we're counting in a more refined way, talking about dimension. And so we have to talk about the algebraic geometric notion of dimension of a variety. And we're saying that this curly C of small circuits is a small dimensional variety, and hence by the suitable generalization of union bounds to the algebraic geometric setting, the union bound will go through and a random set will be a hitting set. Okay, and so that's kind of the sketch. I mean, there's a lot of things one would need to do there. Okay, so, but this result is non-explicit. It's saying that hitting sets exist, but it's not saying anything about the how to construct them. Okay, so then the question would be, can we construct small hitting sets? Okay, and so what is known? Well, one of the celebrated works in this area is the work of Cabinets and then Pangiazo, which for convenience, I will be stating in characteristic 0. So suppose that the n by n permanent, right, that's the hard polynomial that's been pervading this semester. We expect it to be very hard. Well, suppose that it requires 2 to the omega n size circuits, right? So this is basically a maximal complexity in the sense that it's easy to show that the permanent has 2 to the O of n size circuits. And here we're saying that that's basically the best that you can do. So suppose that that is the best you can do. It's maximally hard. There's no real non-trivial algorithms for the permanent. Then this implies that there are explicit n to the order log n size hitting sets for n variable degree at most d, size at most s circuits, where d and s are polynomially bounded, which is the regime that we're interested in. Okay, and so how should we think about this, right? Well, this first assumption is a hardness assumption, saying that something is hard, and something is in some sense maximally hard. And the conclusion of this is a kind of a randomness result, or rather maybe a de-randomization result, but it's usually called hardness versus randomness. And this is basically a quasi-polynomial sized hitting set. So it's not polynomial sized, which is what the Heinz-Schnorr result would say exists. It's quasi-polynomial, so it's qualitatively a little bit weaker, but it's close-ish to the right result, or the desired optimal polynomial sized result. And so this is saying that all we really need to do would be to prove that the permanent is hard, and then we can solve PIT. And in some sense, this result, there are converses to some extent, which is that if you suppose that you have a hitting set for some class curly C of size strictly less than n plus d choose d. So why n plus d choose d? Because that's the dimensionality of a polynomial of n variables in total degree at most d. So if you save just one point on a hitting set, then you can construct some polynomial f not in C. Okay, and again, so this first assumption is a randomness assumption, that you can de-randomize something, and then the conclusion would be a hardness. It's not saying that the should say in time polynomial in n plus d choose d. So it's not saying that the permanent is necessarily hard, but it's saying that in exponential time, we can compute something which is outside of this, outside of some class that you're interested in, which is a very non-trivial result to say. And I'll mention that, in the Cabinet Simplify as a result, I'm stating for a certain set of parameters saying that the permanent is exponentially hard, but you can obtain different results by weakening the hypothesis and getting suitably weaker conclusions. Okay, so what do these two connections, this hardness versus randomness connection, say? Well, basically, this is saying that solving PIT just requires proving lower bounds. Okay, and so in some sense, it's like, well, is PIT like really a new subject? Should we be thinking about this, differently than lower bounds or whatever? But this connection is not quite tight. Number one, right? We only get, for example, quasi-polynomial size in this particular setup. And furthermore, these are not exactly converses of each other. But more of the problem is that, well, as we've seen, like there are some lower bounds for some models of computation, but that's all we know. All we know are lower bounds are only known for restricted models, right? So we don't know that the permanent requires exponential size circuits, and that seems like a very difficult problem. And so obtaining polynomial identity testing, requires a lower bounds, and we only know lower bounds for restricted models. So just obtaining PIT is not, with this connection might be difficult. And what's more problematic is that even though we do know some lower bounds for restricted models, hardness versus randomness, like these connections, especially that Cabinet Simplify results, they often cannot or do not obviously be instantiated in restricted models. Okay, so what do I mean by that? I'm saying the hypothesis here is saying that the permanent requires 2 to the omega n general circuits, and the conclusion is that we have a PIT against general circuits. But what if I said, the permanent requires 2 to the omega size, 2 to the n omega sized, non-commutative formulas or something like that? Is it the case that we get polynomial identity testing for non-commutative formulas? And the difficulty is that that's not necessarily true, because the non-commutative formulas might be too restricted to actually instantiate this connection. So even though we have lower bounds for many restricted models, we can't necessarily, in many cases, just plug in the Cabinet Simplify result to get a PIT algorithm. Oftentimes, we actually have to do more to obtain those results. Okay, so what is in fact known then? What do we know about PIT? There's many non-trivial, in the sense that they're either polynomial time or quasi-polynomial time, or maybe they're just like sub-exponential time. There's many non-trivial white box or possibly black box deterministic PIT algorithms. For restricted models. Okay, and so, one idea would be to use hardness versus randomness. And if you have a sufficiently strong model you're proving lower bounds for, like constant depth formulas, then you can just instantiate the hardness versus randomness, as was recently done by LSD. But in many cases, you don't have a strong enough model. And so what would be the general idea that one would pursue to prove an identity testing algorithm? So there are many different themes. It's hard to really summarize it succinctly, but the way I came up with it would be the following. We're going to reduce the number of variables. So remember, we start with n variables, which is kind of our large parameter. Usually the degree and the size are controlled by n. So we want to reduce the number of variables. but the degree and the size are not actually going to change. We're going to just reduce the number of variables. Reduce the number of variables while what I'll call preserving structure. Okay, and so what do I mean by preserving structure? So one thing of what I would mean would be to exactly preserve the complexity measure gamma used in lower bound proofs. So recall, like in Ramprasad's talks, for example, on lower bounds, and the idea for lower bounds is to come up with some measure gamma, which is small on efficient computation and is large on something like the permanent. And so if we have such a measure, which is small in some sense on efficient computation, what we can try to do is reduce the number of variables while exactly preserving this measure. And why is this helpful and why is this possible? So why is it possible is that the measures we're interested in are saying that the gamma of some sort of small restricted circuit is small. That's why it's useful for lower bounds in the sense that it's small on efficient computation. But because it's small in this context, it's not expensive to preserve. So that's kind of hard to really fully describe, but kind of the idea is that you're trying to preserve all of the information in this small circuit, and you're quantifying that information by the gamma measure. And so if you just make sure that your reduction, just a small number of variables, preserves everything going on in the gamma measure, then it's not going to be expensive. You don't have to pay very much because there's not that much information to preserve. But then why is this useful? Well, generally, the idea would be that if you have a non-zero polynomial, the gamma measure should be strictly bigger than 0. And so this should say that non-zeroness is preserved. And of course, you could just say, well, let's just reduce the number of variables while preserving non-zeroness. I mean, you could say that, but that's kind of too weak a solution concept to say imply induction. So if you want to apply inductive methods, you have to have a strong enough induction hypothesis. And this is kind of the way to state that induction hypothesis correctly. Okay, so this is kind of how I think of some PIT algorithms. But okay, so once we've done, so okay, we reduce the number of variables, preserving structure, but we're not done. We just reduce the number of variables. And so now the second step would be to brute force PIT of polynomials in a small number of variables. And kind of the idea is that, you know, these brute force methods, like that we saw earlier in terms of either the white box or the black box algorithms, those are exponential time in the number of variables. And so if the number of variables is small, it's a constant or logarithmic, then it's actually not that expensive to do these brute forcing. And so that's how you would kind of do PIT. Okay, and so what models do we kind of know PIT for? So I'm not going to give full references to the many authors involved in this. I apologize to them. But for example, there are sparse polynomials of just in a few variables. And so white box here is trivial in the sense if I give you a sparse polynomial, you can just look at all the coefficients and say, is it 0 or not? But black box PIT is slightly non-trivial. There's constant fan-in, sigma pi, sigma thing, top fan-in, depth-free formulas. There are so-called read-once models, which we'll feature later in this talk, in the sense that you have some model where you're maybe only quote-unquote using a variable once for some definition of using. And so there are formulas, there's read-once ADPs, and then there's read-once determinants, which read-once determinants are, for example, relevant in the matching problem. There's say depth-free powering formulas, which was have been discussed. There's non-commutative, say, for example, formulas with divisions related to some of the left-right action stuff that's been talked about, and non-commutative algebraic branching programs. And most recently, very nice work, there's constant depth formulas. Okay, there's others that I'm probably forgetting. Apologies to that. Okay, so there's like these various models, like they're not like, there's no one master model that's like encompassing all of these. But you know, these are the types of models, and they, to some extent, one can massage the proofs into kind of this kind of framework. Okay, yeah. Okay, so this is polynomial ideas.
So, but the original proofs are not, do they have this kind of a structure also, or the original proofs are not in the structure that you laid out?
I mean, some of the original proofs are like, I mean, sparse polynomials are pretty obvious in the sense that you just hash to a univariate and like you're just doing some sort of hashing. I mean, the top Bannon depth 3 formulas, like at least in the black box setting, you're just reducing to a small number of variables, and you just need to show that that works. And the main thing that is an issue is understanding the complexity of these simple circuits and so on. I don't think it exactly follows the complexity measure approach. I think it's, I mean, I think I'm losing a lot of information by saying this thing, but this is kind of how, I mean, I don't know, I was trying to find some unifying perspective, and this is all I could really come up with. Okay, so this is PIT, and so then the question I want to then address is what are the connections to algebraic geometry? Okay, and so the way I want to think about it is, suppose that we have the space of all polynomials and n variables in degree d. So this is all polynomials. We can then look at size f circuits. Okay, and so this will be the 0 polynomial down in the bottom right corner. And then we have curly C, which is say size at most S circuits. Okay, we can look at the map that sends F, a polynomial in this space, to this set of evaluations, and I'll call this just this map H, just to it's an abusive notation, but just evaluate the polynomial on all points in the hitting set. Then we can think of this map as something like the following, where these tuples live in an H-dimensional space, and we can ask, like, what does the map do with the circuits? And so this looks too big in this thing, but here we have the 0 tuple. So clearly 0 is going to go to 0. But what happens to C? Well, you know, this is kind of H applied to C. Okay, and what do we know if we have a hitting set? Well, if H is a hitting set for C, then H is injective at 0 with respect to C, in the sense that the only way you go to 0 here is if you were 0 to begin with. There's no collisions at this 0 point. And so the way I want to think about this is that this is saying that this map from this very, very large space, exponentially large space, to this somewhat small space is preserving some of the structure of C, just in the sense that it's injective 0, but it's not necessarily, you know, but it's reducing the dimension by a lot. And so this is in some sense a dimension reduction result. And preserving injective at 0 is maybe doesn't seem interesting, but we can amplify this as follows. So suppose that H is a hitting set for size at most 2S circuits. Then this implies that H is a hitting set for F minus G, where F and G are size at most S, right? Because if F and G are size at most S, then F minus G is size at most 2S, so it's certainly a hitting set there. And if you hit all the differences, then it implies that H is injective as a map now, thinking about this dimension reduction map. This map is injective on size at most S circuits. Okay, so what's going on here is that injective at 0 seems very weak, but we can look at the differences, and being injective at 0, the differences is saying that in fact the entire map is injective, and so you're exactly preserving there's a bijection between C and its image, and that seems like a very strong notion of preserving a variety, right, while reducing the dimension. Okay, and so this is called, if you have this property, this is called an interpolating set. Okay, so this is kind of a very strong notion of, stronger notion of dimension reduction, preserving the structure of C. And so because it follows from hitting sets, I'm mostly going to focus on injectivity at 0, because that suffices by this argument. So how does this connect to algebraic geometry? Well, there's this fundamental lemma in algebraic geometry known as the normalization. I'm just going to state slightly standardly. So if you have a variety in capital N dimensions, but itself the variety is at most, say, S dimensions, then a random linear map L, sort of pseudo notion of random, from capital N dimensions to S plus 1, so take 1 plus the dimension of the variety, is injective at 0 on V. Okay, so what this is saying is that this is something that's used a lot. I mean, it's usually stated in integral subrings or something. But it's basically saying that there is a dimensional reduction which is injective at 0. And this is something that powers a lot of algebraic geometry in terms of like proving the null-Snellen sets and whatever. And so the question that Catan Mobley came up with in 2012 is basically saying, well, look, this lemma looks very similar to coming up with EIT. But here we're doing it for an arbitrary variety. Here we're doing it for a specific variety of circuits. And so his question was to de-randomize the nether normalization, which is NN, for important varieties. Okay. And why is this interesting? Well, one is we're going to generalize PIT kind of to general algebraic geometry. We don't just have to talk about the varieties coming from circuits. We can talk about any interesting variety and say, can we de-randomize nether normalization for that variety? And so it gives us kind of new questions to address. Nether normalization is also fundamental in algebraic geometry. So maybe there's some idea that gives us new insight into computational algebraic geometry, for example. And then this question is also, as we'll kind of see, related to classifying classification problems in geometric invariant theory. Okay, so what I want to do now is talk about like one variety where we know some pretty interesting things. So let's see that variety. So this is going to be a group action. So simultaneous conjugation action of invertible matrices. So it's, I'm going to switch to characteristic 0. So n by n invertible matrices over the complex numbers on n by n matrices, or we have R matrices, each of which are n by n. So this is the simultaneous conjugation action. What does it look like? Well, you have a tuple M bar, so it's a tuple of matrices. So it's M1 up to MR. It's sent to P M1 P inverse P MR P inverse, which I'll abbreviate as P M P inverse. Okay, so I'm basically taking every matrix and I'm simultaneously conjugating it by the same invertible matrix P. So what will be some examples here? We have the 2x2 identity matrix. This is just like this. Then P identity P inverse is always just the identity. So that's not super interesting. But if we take, for example, the following conjugation. So we have this matrix and we conjugate it by these two matrices. this is actually equal to 1 epsilon delta 1, verifying the privacy of your own home. And so this implies that if we look at the GL2 orbit of this point, 1 epsilon 1, for epsilon not equal to 0, then this is just all the matrices of the form 1 different than 0, 1. So this is the orbit under this action. But we can also look at the closure of this thing. And when you take the closure, we get just now everything arbitrarily close to 0. So this is the closed orbit, and we see that the orbit and a closed orbit are different. And because we're mostly be working with polynomials, we'll mostly be interested in the closed orbits. And so how do we understand, first of all, why is this a variety? Well, we can recall some things that were discussed earlier in the semester. So a polynomial f on the tuple is invariant if f of Pm P inverse is equal to f itself. So when you conjugate the formal variables with some matrix P for all P in GLN, when you conjugate with a matrix, that it doesn't change at all. Okay, and then the set of invariants in this case is denoted CM. So this is the set of polynomials in these tuples, but then we're going to put GLN C in the exponent to indicate that we're only picking the invariant polynomials. And one of the things that was mentioned is that the set of invariants under this action is a ring, and it's finitely generated as an algebra. Okay, so every invariant can be written as a polynomial in a small number, or as in a finite number of generating invariant polynomials. And so the idea is that those finite set of generators for this algebra kind of tell you everything that you kind of need to know about arbitrary invariants up to the algebra generation action. What's more interesting, or another thing that's relevant here, is that we can look at this GIT quotient of C n by n, the n by n tuples, quotiented out by this action. Okay, and then this GIT quotient is a variety, in the sense it has the structure of a variety, where the regular functions defined in this variety are the ring of invariants. Okay, so what this is saying is that this is a variety in some sense, and so we can try to de-randomize nether normalization for it. So can we do de-randomized nether normalization for this variety? And so why is this interesting? Well, for r equals equal to 1, this has actually been seen in the semester so far. We can basically take one matrix and send it to the coefficients of the characteristic polynomial. The characteristic polynomial is invariant, and all these coefficients are invariant. And this basically captures all you need to know about these invariants of M. In particular, it tells you all you need to know about the orbit closure, okay, by the coefficients of the characteristic polynomial. And so this is something which is kind of classic, and so we're just asking to generalize, right? Can we do this r greater than 1? Okay, and this is a de-randomization because there's not that many coefficients, even though there's like infinitely many invariants. This is a very small number of coefficients matching the dimension of the space. It's a de-randomization. So what we're asking is, can we de-randomize it for r greater than 1? Okay, so let's recall some of the invariant theory that we've seen, and how to use that to talk about what does de-randomization mean in this case and how to proceed with that. Okay, so the first thing to remember is that invariants are constant on orbits and hence orbit closures. Okay, so if I want to prove to you, for example, that 2 points are in different orbits, I can just, or orbit closures, I could just give you an invariant where the disagrees on those 2 particular points. And that implies that they're actually in different orbits. And more generally, we had the theorem that if we look at the GLN orbit of a tuple A of matrices, and we took the closure, and I apologize for this notation. So this bar means that this is a tuple of matrices. And then this bar means we're taking the orbit closure. So it's two different bars. It's but if we look at the orbit closure of the point A, and we look at the orbit closure of the point B, then this is a non-empty intersection if and only if there's some invariant in the ring of invariants such that F on A is different than F on B. Okay, and so basically what we're saying is that the orbit closures are in some sense the points of the variety. These are the points that the ring of regular functions can distinguish. Okay, and so we're basically trying to understand what are these points, how do we classify them, how do we work with them? And so we could work with basically all of the invariants at once, but there's infinitely many. And so there's kind of the idea that we want to reduce the set of all invariants to a set of small number of invariants that capture exactly this question of, does there exist an invariant that separates two particular points? So the particular goal that Melanie asked is, given two tuples A and B, decide if there exists an invariant that separates them. Okay, so this is basically saying, are the orbit closures, do they intersect or do they not intersect? Okay, so this is not quite exactly a dimension reduction result. And so, but it's kind of asking to kind of classify orbit closure intersections in some way in an algorithmic sense. So to talk about a real dimension reduction, we need to give a stronger solution concept, which is the following. Suppose we have curly S, it's a subset of invariants. We'll call this as a set of separating invariants. If what? If for all tuples A and B of n by n matrices, there exists an F in the entire ring of invariants that separates A and B, in the sense that F of A is different than F of B, if and only if there exists a G in our smaller set of separate invariants that also separates A and B. Okay, and so what this is really saying is that instead of talking about all invariants at once, we can simply restrict to the set of separating invariants that decide, does there exist a separating, does there exist a separating invariant that differs? And so what do we know? Well, we know, previous slide, that the ring of invariants is finitely generated. So there's some finite list of generators that tells us kind of everything we need to know about the entire ring to some extent. And it follows that if a set S generates the ring of invariants, then S is a separating set. Okay, basically because the generators kind of tell us everything we need to know. And in particular, it says that a finite set of separating invariants does exist because we know the ring is finitely generated. And so then the goal would be to construct a small set of separating invariants. And this is our dimension reduction, in the sense that we start with an arbitrary tuple. We start with tuples of matrices, and we can map those tuples of matrices to their orbit closure, which is basically saying that we take that tuple of matrices and we map it to the point in the GCT quotient, which is basically the evaluation of every invariant on this tuple of matrices. But there might be many, many invariants that might be really big, and so that's not very helpful. What we want to do is we want to construct a small set of the separating invariants that tell us everything we need to know about the orbit closure. And that's going to be much better than the set of all invariants, which is maybe. Okay, so let's see some examples. So let's look at the trace of M1. So we have R matrices, but let's just look at the trace of the first matrix. Well, under this action, of simultaneous conjugation, we get trace of P M1 P inverse, right? And if you put your linear algebra hat on, you remember that trace is cyclic, and so this is in fact equal to trace of M1 P inverse P, and then P inverse P cancels, and this is trace of M1. Okay, so the trace of the first matrix is invariant, right? The determinant of M1 would get mapped to determinant of P M1 P inverse, which when you use multiplicity of the inverse of the determinant is then the product of the determinants, and these cancel, and you get back the determinant of M1. Okay, so the determinant also invariant. We can also consider so-called trace monomials, where we take M1 times M2 times MR. Now we're involving multiple matrices at once. So we take the product of all these matrices, then we take the trace. Then what do we get? This gets mapped to the trace of P M1 P inverse, P M2 P inverse times ... P MR P inverse, right? And the P inverse P will cancel here, P inverse P will cancel here, and then the P inverse will also cancel because trace is cyclic again. So this is also invariant M1 to R. Okay, so these are all invariant polynomials, and there's a theorem of Borghese, Razlov, and Formanek, which says that basically this is not all there is to say, but this is a generating set. These sorts of trace monomials. So the ring of invariance is generated by the trace monomials, which I'll call curly T, trace of MI1 up to MIL, where 1 is less than ij, less than r. So each of these is just some matrix in our tuple, and L is at most n squared. So 0 at most L is n squared. Okay, so this is some finite set of trace monomials, which generates the entire ring of invariance. And in particular, it's exponentially large. Okay, so the corollary of this, based on what we've said so far, is that there exists an explicit exponential and NR size separating set of separating invariants. And so this is the, and in particular, this implies an exponential time orbit closure intersection, sorry for writing so small, algorithm. Okay, so this is saying there exists an exponential time algorithm to decide orbit closure intersection, and there exists an exponentially large set of separating invariants. And so the picture here would be that like we start with C n by n R, right? These are the tuples that are going on. And then we can map this to F exponentially large, where this is the set of all, like we take any tuple and we evaluate every generator at this tuple, okay? And this is the embedding that shows that the GIT quotient is a variety, okay? But this is really, this is not that large in dimension, right? It's like n squared times r dimension, just based on parameter counting. And this is like really big dimension, exponentially large, right? So the image should really only be quite small, right? Just by, I mean, maybe it should be like this, but this is really small and compared to this. This is like, n squared r dimensional, which is much, much smaller than exponential n r. So what we want to do is we want to map down to a smaller space of size polynomial in n and r, which preserves the relevant structures of this variety and hence is a dimension reduction. That's what nether normalization is asking. And so how do we do that? How do we go from exponential dimension to polynomial dimension? Basically, we're going to do it using polynomial identity testing. Hopefully I can finish this in the next 7 minutes. Okay, so how do we do that? Well, the key construction, this is from a work from myself and Amir from 2013, the first of the 2 papers in that year. Okay, so this is a construction. So given M1 up to MR as formal polynomials and formal matrices, we can first define M of X as the sum I from 0 to R of mi x to the I. So X is a new variable, and this is a univariate polynomial with matrix valued entries. And note that I only have R matrices, but I'm indexing from 0. And so I'm going to say that M0 is just defined to be the n by n identity matrix. Okay, so this is a univariate polynomial with variable X, and it's matrix valued. The coefficients are matrices. We can then define the f sub L Forbes-Explicit polynomial. I don't know what to call it. Why not? As follows. We take the trace of this univariate polynomial, matrix valued polynomial, in some variable x1. And then we take the same univariate polynomial, but now in a new variable, x2. And then we keep on going up to variable xl. So it's the same matrix valued univariate polynomial, but in different new variables each time. We take the product of those things. It's again a matrix, and then we take a trace. So this is a multivariate polynomial in the x's. And we can also view this as a polynomial in the m's as well. And what's the structure of this? Why is this interesting? Well, for any L and evaluation point alpha, we could evaluate this Forbes-Explicit polynomial at alpha. We take X and we evaluate it at alpha. And so now this is a polynomial in M alone. And if you think about it, this is invariant. This is an invariant under simultaneous conjugation because we basically just have a bunch of traces. Okay. And so then the key lemma proposition maybe is the following then. Like, why am I defining it this way? Well, suppose that you have A and B, 2 tuples. It's going to be separated by some invariant if and only if you take the Forbes-Explicit polynomial with parameter L being n squared on our tuple A with indeterminant x. So this is a formal polynomial in x, but because we evaluated in A, it's a polynomial in x alone. It's a separated by invariant if and only if this polynomial differs from the polynomial when we evaluated B and with the same indeterminants in x. So this is a polynomial in x, and we're saying that it's separated by invariant if and only if these 2 polynomials differ, which means that all the coefficients differ. Okay, and so what's the proof? Well, the backwards direction is basically this lemma. Basically that if these 2 differ, then because this is an invariant, then if these 2 differ, there's some point where they differ, and hence you get an invariant that differs. The forward direction is maybe what's more interesting. Well, what do we know? What do we have? Right? We have that there's an explicit set of generators, and those generators form a set of separated invariants. So because of that, if there's any invariant that separates A and B, then A and B is separated by some trace monomial. Right, some trace of mi1 ... mil, or some L at most n squared. But what is this trace monomial? This trace monomial is equal to the coefficient of x1 to the I1 ... xl to the IL in the polynomial f n squared in x. So let's look at this master construction. It's a generating function which takes all of the trace monomials and like embeds them into one thing. And if we look at the coefficient of this x1 to the I1 dot 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 xl to the IL, then we exactly get this trace monomial, right? Because if you look at the x1 to the I1 coefficient, then you're just pulling out mi1, and that's why you're getting mi1. In x2 to the I2, you get mi2, which is then what's here. And so basically these trace monomials form all of the coefficients of this Forbes-Explicit polynomial, and that's all the coefficients that this polynomial even has. And so it's saying that, well, if A and B is separated by some trace monomial, then one of the coefficients, one coefficient of this polynomial differs. And if a coefficient of the polynomial differs, then it's exactly saying that these two polynomials are different. So that actually exactly implies this result. Okay, so it's a bit fast, but that's how it works. And now let's just quickly go over the corollaries of what this implies. So Momley first observed that basically what this sort of thing implies is that to decide if there's any invariant that separates them, it reduces to whether two polynomials are different. And so this gives a randomized polytime algorithm for this orbit closure intersection. Basically by applying the Shortstop Dilemma to obtain a randomized algorithm PIT to solve this PIT problem. Okay, but Momley gave a slightly more complicated generating function. And so the class of PIT that he would need to de-randomize was slightly more complicated. And so what we did is we improved the construction, which is the one I gave here. And what you end up getting from that is that if we look at any A and B, and we look at the difference of these Forbes-Explicit polynomials in A minus B, this is a polynomial in N and R size read once oblivious algebraic branching program. Okay, so this, I'm not defining this model, but I kind of alluded to earlier how read once models are things that are restricted and we know how to do for lower bounds in particular. And one of the things that is known, for example, due to methods from Nissan, is say that the n by n determinant requires 2 to the omega n size read once algebraic branching programs. So this is a class that we know how to prove lower bounds for, and that's something that follows from Ramperzad's talk in the sense that read once branching programs are essentially non-commutative. They don't exploit commutativity in any way. So we know lower bounds for non-commutative polynomial, non-commutative APs, and so those lower bounds lift to this read once setting. So the fact that we know lower bounds should say that, well, we should know more things. And indeed, Raj and Stilka in 2005 and different result of Arvind Jaglikar and Srinivasan in 2009 showed that there's a polynomial time deterministic white box PIT algorithm for read once ADPs. And in a different work from the same year of myself and Amir, we showed that there's a quasi-polynomial time black box PIT for read once ADPs. And so instead of applying the randomized Schwarzschild lemma to only obtain a randomized polynomial algorithm for this orbit closure intersection, we can instead apply these deterministic algorithms. And then what we get, final statement of today, is that first of all, there is a deterministic polynomial time algorithm for the orbit closure intersection for simultaneous conjugation. And then maybe more interestingly is that there's an explicit polynomial in n r to the order log n size set of separating invariants for the same action. And so the kind of the point is that this is an overclosure intersection. This is some sort of algorithmic question. But the set of separating invariants is really the type of dimension reduction that I've been talking about, maybe over here, where I want to, instead of talking about an embedding of this variety in an exponentially large space, we can instead embed this variety in a smaller space. And the dimensionality we're achieving is not the optimal one, which would be polynomial, but quasi-polynomial. And so it really is a dimension reduction for varieties that we're seeing. And then I'll just stop with one remark. So on Tuesday, KB talked about kind of null cone actions for left-right actions. And we saw this analogous results for the null cone of the left-right action, where it's not quite solving, the null cone is not quite the orbit-closure intersection question, but it's similar. And so there, in those settings, like they're obtaining algorithms. Like I give you something, is it in the null cone? Okay, but so I missed something. My understanding is that there's no separating invariance known, no explicit. In the sense that we're giving you a way to decide whether something is in the null cone or not, but it's not a set of invariants that always separate the null cone from things outside the null cone. And this is basically in the sense that those works are solving a white box PIT algorithm, but to obtain these separating invariants, you would need a black box PIT algorithm, which is still currently open. And so at that point, I'll just conclude. Thank you.